again, and we're going to continue mm, dealing with the complex reactions problems. And here is another problem for your consideration. It's going to appear on the screen of your computers in a few seconds. Hold a second, please. Yeah, here it is. So again, we've got a system in which a unimolecular consecutive reaction occurs. A turns into B, which turns into C. Well, and we've got the concentrations of all the participants of the reaction at time t, which is equal to 2.5 minutes. And they ask us to solve the inverse task, the inverse problem of the chemical kinetics. So what does it mean to solve uh, an inverse problem of chemical kinetics? It means to calculate the magnitudes of K1 and K2 rate constants, and preferably, if it's possible, on the basis of the data given, to work out the mechanism of this reaction. But in this particular case, all we need to do is to compute the values, the magnitudes of K1 and K2. Okay, so the picture is quite clear. The thing is that, as it is a unimolecular reaction, it makes the situation easy to deal with. We can use the material balance equation in order to calculate the initial concentration of the reagent A. Here it is. At any moment t, the initial concentration equals to the sum of the concentration of the reagent at a moment t plus that of intermediate B plus that of product C. Okay, we've got all these three values, which means that we can calculate the value, the magnitude of the initial concentration of the reagent A. Let's do that. So 62.5 plus 17.5 plus 20.0, and we've got 100, right? Yeah, and we've got 100. 100 moles per cubic meter. Okay. Then we remember that for this part of the kinetic scheme, we can apply this formula. It's K1 equals 1 over T times logarithm to base E, or in other words, natural logarithm of the ratio of the initial concentration of reagent A to its current concentration at time t. So we've got all necessary magnitudes to do the calculations. Let's substitute them into the formula. We have just calculated the initial concentration. Okay, and my calculator says that um, the uh, rate constant of the first reaction is equal to 0.188 minutes raised to -1. Okay, why -1? Because it is a unimolecular reaction. Okay, now knowing K1, we can actually calculate K2 if we remember the formula, which enables us to calculate the current concentration of the intermediate B. Let's copy it out here. So B at time t equals K1 times the initial concentration of the reagent A divided by K2 minus K1, okay? And this fraction is multiplied by um, the difference exponent raised to minus K1 times T minus exponent, another exponent raised to minus K2 times T. Okay, so let's do that. We have just calculated no. No. Um, let let us plug in all the values we've got. So BT is equal to 17.5, right? We have just calculated K1 is 0.188. Okay. The initial concentration of the reagent is equal to 100. So K2 minus 0.188. Okay, then exponent minus 0.188 times 2.5 minutes minus exponent of 2.5 minutes times K2. All right. So after very simple algebraic uh, let's say transformations of this equation, we finally get the following transcendental equation: 0.625 minus exponent raised to minus 2.5 times K2 equals 0.931 times K2 minus 0.175. Yeah, again, a very serious question arises. So how can we get the root of this problem? The thing is that it's not a typical simple algebraic equation, and we cannot apply Viet theorem to get the root because we've got the exponent. Well, the only thing to do with in this particular case, if you don't know how to program, so in this case you can use the Excel in order to get at least approximate value magnitude of the root K2. So my calculations shows that K2 equals 0.647 minutes raised to minus 1. These are the answers to this problem. K1 equals okay, sorry, 0.188, while K2 equals 0.647 minutes raised to minus 1. Now let's proceed to the next problem. It's about um, a series of parallel reactions. Yeah, we've got a system in which a series of parallel reactions occur. The first parallel reaction is when A transforms into B, and it's got its rate constant K1, while the other reaction which occurs in the same system is when A transforms into C, and it's got its own rate constant K2. In other words, we've got the reagent A, and the system has got two products, B and C, okay? Now, what else? The problem says that at a particular moment t, the system contains the mixture of the products, and the products again are B and C, and the concentration of B is equal to 35% or 0.35, because normally in chemistry and physics we deal with not percentage but with mm, fractions, right? Well, and the concentration of A halves within 410 minutes. In other words, it's half time of for A, tau, it's the Greek letter tau. So tau for A is equal to 410 seconds. Well, and they ask us to calculate the magnitudes of rate constants K1 and K2. Now, let's do that. Again, I'm referring to one of the previous lessons where I derived the main formulas we normally need when we deal with complex reactions. And in this particular case, we are going to choose the formulas which are related to parallel reactions, okay? And in this particular case, it's this one, the natural logarithm of the ratio of the initial concentration A to its concentration at a particular moment t equals the sum of the rate constants times t. Okay. What does it mean? Tau. Tau means that the concentration of A at this moment is equal half of its initial concentration, right? So let's substitute this into this place in this formula, and what do we get finally? This one, yeah. And again, the sum, I'm sorry, the sum of these um, rate constants times, but now not t, but tau. Yeah, okay. These cancel, okay. And here we got 2. In other words, at this particular moment, we can calculate the sum of the two constants. So K1 plus K2 equals natural logarithm of 2 divided by tau for A. Um, uh, the natural logarithm of 2 approximately equals 0.693 divided by 410, and we get 0.00169 seconds raised to minus 1. Okay, then yeah, I should have said that these two parallel reactions are unimolecular. For that reason, the measurement unit is seconds raised to minus 1. Okay, now we also remember the formula that K1 divided by K2 is equal to the concentration of B, right, to the concentration uh, of C. But C, the measurement units of C, moles per liter or moles per cubic meter, right? But we've got percentage here. But the problem is that the way out of this problem is that C is proportional to omega. For that reason, we can substitute it. It's okay. And if the mixture is composed of the two elements A and B, um, omega C is equal to 1 minus omega B. It's very good. 0.35 and 1 minus 0.35 gives 0.65, right? And this ratio equals, let me have a look, um, 0.5385. In other words, K1 equals 0.5385 times K2, okay? So we've got a a very simple system of two equations, K1 equals 0.5385 times K2, and the sum of the constants equals 0.00169. We can substitute K1 with this expression, and finally we've got the following very simple algebraic equation: 1.5385 times K2 equals um, 1.69 times 10 raised to minus 3. 1, 2, 3. Yeah. Okay. Now we can calculate K2. It's equal to roughly 1.99 times 10 raised to minus 3 seconds. Raised to minus 1. And now we remember that K1 is equal 0.5385 times K2. Instead of K2, we have just found out its magnitude. It's 1.99 times 10 raised to minus 3. And we've got the answer for K1. It is 0.592 times 10 raised to minus 3. These are the answers to this problem. Okay, let's proceed to the next problem. So we've got a system in which a reversible reaction occurs. Reversible means that A transforms into B and B in terms transforms into A. And we've got the rate constants for the forward and reverse reactions. So K1 is the forward rate constant, and it's equal to 300 seconds raised to minus 1, while that for the reverse reaction K2 equal 3 times as little as K1. Okay. Also, the problem says that the initial concentration of a product, and again, product is B. The initial concentration of the product of this reaction in the very beginning is 0. And we are supposed to calculate the time when the concentration of the reagent A falls twice. Okay. In other words, when the concentration is equal a half of its initial concentration. So that's it. Now, what are our first tips? First of all, we should pay attention to the fact that we are dealing with a reversible reaction. And let's write down the formula for a reversible reaction. Here it is. It means that we're supposed to get the magnitudes of x of infinity. What does mean x of infinity? This is the drop in concentration of the reagent A when the system is at equilibrium. Let's do that. So I'm writing down this scheme of this reversible reaction. In the very beginning, we've got the initial concentration of the reagent A. Let's symbolize it with letter A, okay? And in the beginning, B is absent in the system, okay? So when the whole system reaches equilibrium, the drop in the concentration of A is equal to x infinity, okay? And at the state of equilibrium, the concentration of the reagent A is equal to A minus x equilibrium, while the concentration of B is equal to S equilibrium, right? In other words, we can write that the concentration of A at the state of equilibrium is equal to A minus X equilibrium, while the concentration of B at the state of equilibrium is equal to X equilibrium, okay? We also remember that the equilibrium constant in this particular case is equal to B, the concentration of B at the state of equilibrium, divided by the concentration of A at the state of equilibrium, okay? And we also remember that K is equal to the ratio of K1 to K2. We've got the magnitudes of these two. And now we see that the equilibrium is equal to 3. So we can write that X equilibrium divided by A minus X equilibrium is equal to 3. And now get let's get uh, X equilibrium from this expression. It's very easy to do, and if you do everything correctly, you should get 3 times A over 4. Yeah, you can do it orally. It's very easy to do. Now we've got this. What about this X? It can be done in the same manner. So we've got A and 0 in the beginning. By some time t, X is the drop in the concentration of A, and at time t, the concentration of A is equal to A minus X, while the concentration of B is equal to X, right? Okay, and we remember that the concentration of AT is equal to the initial concentration of A divided by 2. But the initial concentration of A is equal to A, while the current concentration of A at time t is equal to A minus X. So let's write it. A minus X is equal A over 2 half A. In other words, X is equal A divided by 2. Now we can plug these two values into this formula instead of x infinity and x. K1 plus K2 gives 400 T. Now, we got A in the numerator and denominator, and they cancel each other. So finally, we've got that the natural logarithm um, of 3. Where to get 3 from? From this expression, for 3/4 divided by 3/4 minus a half is 1/4, and 3/4 divided by 1/4 gives 3. For that reason, I wrote 3. So the natural logarithm of 3 is equal to 400 times t, and t equals natural logarithm 3 divided by 400 is roughly 0.0027 seconds. This is the answer to this question. Now let's proceed to the next problem. Um, so we've got a system where a unimolecular reversible reaction occurs. A transforms into B and vice versa. B transforms into A. And we also have the magnitude of the equilibrium constant for this reaction, which is equal to 8. And we also know the magnitude of the rate constant for the forward reaction, K1, which is equal to 0.4 seconds raised to minus 1. Okay. Now, we are supposed to calculate the time when the concentrations of A and B are equal to each other. So we're supposed to calculate this time t. Now, again, as we are dealing with a reversible reaction, we somehow should start with getting the magnitudes for x infinity and x, okay? And to do this, we need the schemes of this reaction, the scheme of this reaction. So in the beginning, we've got the initial concentration of A, while that for B is equal to 0. Now, when the system is at the state of equilibrium, the concentration of A is equal to A minus X infinity. Again, what is it? X infinity. This is the drop this is the fall in the concentration of A. Um, okay, and the concentration of B at the state of equilibrium is equal to X equilibrium, right? So in other words, we've got the following picture. Okay. Yeah. Then we remember that K, um, the equilibrium constant is equal to the concentration of B at the state of equilibrium divided by the concentration of A at the state of equilibrium. Okay. And we know that K, capital K, is equal to 8. And we can express X equilibrium through A from this expression, and it's equal to 8 times A divided by 9. Okay, now we've got X equilibrium. Now we're going to get X using the same scheme of this reaction, A 0 X. Um, the problem says that the concentration of A at time t is equal to concentration of B at time t. In other words, A minus X is equal to X, because A minus X is the concentration of A at time t, while X is the concentration of B at time t. And according to the problem, these two concentrations are equal to each other. It means that double X is equal to A, and X equals um, half of A. Okay, now we are ready to proceed to the calculations using this main formula for reversible reactions. We need to compute this one. It means that T is equal to 1 over the sum of the two constants times natural logarithm of this ratio. Okay. We've got the no, we don't have K2. It's not a big problem to calculate. K2 is equal to K1. No, on the second place. Capital K is equal K1 to K2, right? Divided. So that means that K2 is equal K1 divided by capital K. K1 it's 0.4. If we divide by 8, we'll get 0.05. Yeah, okay. And it means that 0.4 plus 0.05 gives 0.45. Okay. Instead of x infinity, we write, where is it? X infinity. Yeah, this one. 8 times a over 9 minus a divided by 2. So a is contained in the numerator and denominator of this fraction. It means that a is cancelled. That's very good. And it means it's logarithm of what? Let's do it. 8.9 minus a half 16 minus 9 over 18, right? 8 means 7. 18 over 18, okay? And now it's 16 over 7. Okay, it means that t is equal, this is what 1 over 1 0.45 is equal to logarithm of 16 divided by 7. And that gives us 1.84, I'm sorry, 84 seconds. This is the answer. Now let's proceed to the next problem. We've got a series of two parallel reactions. A turns into B, and it also turns into D. In other words, we've got two products, B and D. Now, the concentration of B in the system is equal to 0.63, and uh, now A transforms by a third. Well, and the time needed for this transformation for A is equal to 7 minutes. And now they ask us to calculate K1 and K2. So let's do that. Again, this is a series of parallel reactions, and we know the formulas. Let's write it down. The main formula for series for parallel reactions um, is the initial concentration of the reagent divided by its current concentration at time t. Well, and this is the sum of the rate constants K1 and K2 multiplied by T. Okay, what should we know about the denominator of this fraction? It's the current concentration of the reagent at time T. We know that as when the time is 7 minutes, a third of the initial concentration transforms. That means that the the rest of the concentration, what we got by 7 minutes, is equal to the initial concentration minus uh, that of A, which has been transformed, right? And this is the coefficient of proportionality, uh, psi. It's a Greek, another wonderful Greek letter. And this coefficient of proportionality is equal to a third. In other words, in other words, we've got that the concentration of the reagent A by time t, which is equal to 7 minutes, is equal to 2/3 of the initial concentration. Okay, 2/3. Okay. Now, we also know that t is equal to 7 minutes. Now we can calculate the sum of the two constants. So K1 plus K2 is equal 1 divided by T times natural logarithm of the initial concentration of the reagent A divided by this, and we have just got that it's equal to 2/3 of the initial concentration. Cancelled. In other words, we got a seventh times the natural logarithm of 3/2, and that gives us the following value. Magnitude of the sum is 5.79 times 10 raised to minus 2 minutes raised to minus 1, because the both reactions are unimolecular. Okay, but we've got just this the sum of the constants, but we haven't got the magnitudes of each of them yet. And now this is what we're gonna do. So K1 divided by K2 is equal to the concentration of B divided by the concentration of D, right? And we've just got a similar problem where we substituted C to the concentration of omega. Okay, it's 0.63 divided by 1 minus 0.63, and it equals 1.7027. In other words, K1 is equal to 1.7027 times K2, right? Now we can substitute this K1 with what it's equal to in terms of K2, and finally we will get that 2.7027 times K2 is equal to the sum which we already calculated previously, 5.79 times 10 raised to minus 2. And now we can get the magnitude of the second rate constant. It's 2.14 times 10 raised to minus 2 minutes to raised to minus 1. Okay, and K1 is now we should multiply 1.7027 by this value, 2.14 times 10 raised to minus 2, and we got 365, roughly. 365 times 10 raised to minus 2 minutes raised to minus 1. So these are the answers to this problem.
Hello, my dear students. Today's lesson is going to be slightly different from the others, and you might have noticed that I'm speaking English. It's because of the great number of my students living in other countries whose native language is English, and they have asked me to translate at least a couple of lessons into English so that they can get what I'm talking about while I'm explaining a solution to another problem. I hope that my Russian students, Russian-speaking students, will not experience great problems, because it's not a great challenge to understand, to comprehend English these days, because English has become an international language around the world. Well, anyway, if some of you haven't been unable to comprehend something, so you may ask me in your comments below the video. Okay, now, however, I want to say that the text of the problem will be in Russian, but the whole explanation will be in English. Okay, what is the way out of this seemingly baffling situation? It is that we are going to use mathematics, and in my opinion, mathematics is a truly international language among scientists, in particular among chemists and physicists, right? For that reason, whatever I'm writing on the board will be comprehensible to everybody who knows mathematics. Okay, now the text of a problem, I'm going to translate it into English right now. We've got a system in which a unimolecular consecutive reaction occurs, and the scheme of this reaction is represented here. And it's also known that the initial concentration of the reagent A is equal to 100 of moles per cubic meter, and the rate constant of the forward reaction is K1 is 0.25 minutes raised to minus 1, while that for the second stage of the reaction is equal to 0.95 minutes raised to minus 1. They ask us to calculate the concentration of the product C at the time when the concentration of the intermediate in the system is the largest. Okay, this is it's what the problem is itself about. Now, in one of the previous lessons, I already derived all the formulas we need when we're dealing to one of the three main cases of complex reactions. In this particular case, we're dealing with a consecutive reaction because we've got the intermediate B, the initial reagent A, and the final product C. Now, also we've got a clue in the problem itself. They say that we are supposed to calculate the concentration of product C at the time when the concentration of the intermediate is the largest, and we know the formula. T max, is equal to the natural logarithm, or logarithm with to the base e of the ratio K2 over K1 divided by the difference between the two concentrates, right? And we know all the values which are incorporated into this formula, and if we get armed with a calculator, so we can get the value of the Tmax. This is the time when the concentration of the intermediate is the largest. So let's do that. 0.95 over 0.25, right, and 0.95 minus 0.25. So, and my calculator says that it is as much as 1.91 minutes. Okay, so that means that at this particular time the concentration of the intermediate, is B, is the largest. And we don't need to calculate the concentration of B itself. Absolutely no need to do that. All we need to do is to know the formula enabling us to calculate the concentration of the product at any time. And again, I want to say that I'm referring to one of the previous lessons where I derived this formula. Here it is. So the concentration of C at any moment t is equal to the initial concentration of the reagent multiplied by minus exponent raised to minus K1 times T, okay, minus, and we've got the ratio of K1 over K2 minus K1 multiplied to exponent to minus K1 times T minus exponent raised to minus K2 times T. Okay, we've got K1 and K2, here they are, okay, and we have just calculated T, the time when the concentration of B is largest. So let's plug in all these values. We know this concentration too. Here it is, it's 100. Okay, 0.25, and instead of T we put 1.91. Okay, then minus 0.25 over 0.95 minus 0.25. Okay, 1.91 minus exponent raised to minus 0.95 times 1.20, I'm sorry, 91. Yeah, okay. So if you get armed with a calculator, you will get the right answer immediately. So my calculator says that it is 21.63 moles per cubic meter. This is the right answer to this question, to this problem. Some of you may ask me, George, why are you using so strange, so add measurement units, moles per cubic meters, because we have got accustomed to dealing with moles per liter. You are dead right indeed. Most chemists and physicists, no, chemists actually, are accustomed to using moles per liter. However, it's not a great challenge for us to do that, knowing that a cubic meter contains 1,000 of liters. That means that this is the clue. If you want to transform these measurement units into something which is more appropriate for you, or which seems more appropriate for you, so it's not a great problem. All you need to do is to divide this value by 1,000 and we will get the right answer in terms of moles per liter. That's it. So this is the first problem. Okay, and now we're going to proceed to the next one. Thank you.